All right. Hi, I'm Josh Marantz. I work on load balancing and Envoy at Google, and this is Otto Vanderschaaf, and we're going to talk to you today about some tools that we've been using and working on to help improve Envoy scalability. So, man, every talk has been a great lead-in. Everybody is talking about how awesome the observability is, and that's exactly our observation as well, that you can kind of put Envoy next to every system within your service-oriented architecture, and you get a ton of visibility. And one thing I really want to point out is that it's a very kind of extensible system that's got support for StatZ and Zipkin and Stackdriver, a bunch of other things, but it's also got a really nice extension architecture so that you can plug in any stats observability system that you want, including proprietary ones. It's one of the themes is that Envoy is kind of visualization agnostic, and it just gives you a ton of hooks to be able to see everything that's going on. So the big question for us is, how does it scale? And the needs of the company that originally built it, Lyft, are not exactly the same as some of the needs of the companies that have been adopting it and will do so in the future. And one thing that really interested us is to explore what happens when you have a lot of tenants or different applications sharing the same proxies. This might happen. You might want to do this if you are using Envoy as a front end to a large internet company or something like that, or as a proxy for a content delivery network or for load balancing. And an interesting point in this space that we just look at as a benchmark is 10,000 clusters, or which is Envoy terminology for a backend service. How does everything work when you kind of go up to those numbers? And so for the rest of this talk, we'll focus on 5 different tools and techniques that we've been using to kind of learn more about that space. So one of the first things that I found when I started to work with Envoy with a large number of clusters was there was some pretty severe quadratic behavior in parts of the system. This kind of pathological situation was actually very easy to spot. In fact, just by hitting Control-C while in the debugger, you not only know exactly where the problem is, but have all the context you need to understand how to solve it. And solving it was, took some time, but was not really all that. It was relatively straightforward and got us a 20x speed up, bringing the startup time from over 10 minutes to 22 seconds. But it wasn't really very satisfying to have to take 22 seconds just to start up a proxy with 10,000 clusters. So we move forward. Once again, at 22 seconds, the problem was pretty easy to spot in the debugger, but profiling tools are really helpful as well. In particular, CallGrind helps you identify like how many times the regular expression library was being called, 10 million. Of course, we don't know why, we still don't know what the best way to solve the problem is. We also don't want to just drop the regular expressions. They were providing a lot of that really great stats functionality, like being able to take kind of a flat list of stats and add some structure to it, which is really good for some of the stats visualization tools like Prometheus and so on. So we knew the problem was regular expressions, but how to solve it was not completely clear. So this brings us to our second method of performance improvements called Annotations. So here we put together a really small library of macros and support functions and use them to annotate the source code where we thought the problem might lie, and in particular the tag extraction regular expressions. So the way that this works is that you first of all have these macros that don't, they compile to nothing if you're not enabling performance annotations, but when you do, you can, the perf annotation macro kind of initiates a timer. Then there's a record macro, which records the time. And in particular, there's kind of 2 bits of annotations that you want here. One of them is a static one, which identifies, in this case, did the code go on the match path or the miss path? And the other one, which was really important, was what exactly was the pattern that it was trying to match when it took a lot of time. So once you have all of that, you can dump out the results into a table, and you get something that looks like that. And then suddenly the clouds kind of parted because, first of all, we noticed that almost all of the high-cost operations were mismatches. So basically, we were spending, so 3 of them were more than the others, but we're spending over 3/4 of the initialization time basically finding nothing, finding, finding stats that didn't match a tag structure that we were looking for. And only one of the kind of significant time consumers, which took about 0.4 seconds, was actually a match that delivered any value. So diving into what the regular expressions actually look like, this was an example of a regular expression which extracted some cluster information and some SSL cipher. And we noticed that this regular expression must begin with a literal string cluster, and it must also include another literal string SSL.ciphers. So you might think that it would be possible for the regular expression library to notice this itself because it is compiled and do something really good when the required literal string is not in there, but it does not. It goes slowly. So it's actually better to do a quick scan ahead of time. And so when we re-annotate the code, we first of all have to split the system into an initialization phase where we build kind of a prefix match. So all of the regular expressions that might match cluster dot would be put into a list, and those are the only ones that we want to evaluate. And then we can also do the skip of the regex eval when the required substring is not in there. So this brings up a very different story. Now all of those misses that were in the original annotation are now gone. The whole thing takes 3.75 seconds, and now we're kind of into a more acceptable range of operation. The question is, do you stop here? And the answer is yes, we actually stopped there. But that's kind of good enough. But for the purposes of this talk, I said, well, why don't we just keep going a little bit further? Because that 0.4 seconds looks like it might be low-hanging fruit. So now we can dive into the regular expression library. Actually, the other thing that happened in the meantime was that Matt added RE2 support to Envoy, which kind of enabled this to occur, which is the other kind of gating item for this particular optimization. So the first thing that we want to do is look deeply at how well the regular expression library is performing. We know that std_regex is not the best implementation for our purposes. It has a lot of platform variance. It actually allocates memory during the matching phase, at least the way that we were calling it in some cases. It's time to bring in microbenchmarks, because if you want to make a decision like moving from one library to another, you want to do so with real data. So microbenchmarking helps measure the performance of a very small and specific piece of code. Google has a microbenchmarking library, which I'm really familiar with, but also there's tons of other alternative microbenchmark libraries that you can find on the web. So these are really good at many phases of development, including when you're first writing code, if you want to evaluate which algorithm is going to work best for a data set that you think you have. And then also when you have identified a potential problem in your code and you want to now try out a solution before you start to make a broader system test where it's harder to discern subtle differences. So this is the exact regular expression that was in place, and I kind of looked at that and thought it wasn't the most intuitive way to write it, so I wrote it a different way, and we can try that one. We can try it with multiple regular expression libraries, see which one works out best, and this is what we came out with. So the starting point was that it took about 1.3 microseconds to evaluate that regular expression on a candidate set of inputs. And actually, that's a pretty small number, and if that was being done once, then you would be done, and that would be fine. But this was being done 1 million times for that one, per regular expression. I mean, for each regular expression, so it was worth optimizing. Just switching the regular expression library to use a string view rather than a string reduced the number of allocations, and that was kind of a very easy way to get 5% improvement. And then switching to that alternate pattern, I thought that was going to make things better with std_regex, but it made it substantially worse. I was surprised at that. I still don't really know why that is. But with RE2, everything was much better. It brought it down to a microsecond for the original form and to less than half of a microsecond for the alternate version that I wrote. So now that basically more than cut in half the time that we spent on that on the longest regular expression, improved the overall startup of Envoy by 10%. Really, for just changing one regex, that seemed worth it. So the takeaways for Microbenchmarks and Annotation is that first you need to run the system with realistic data to learn where the bottlenecks are, and then you can start bringing in the microbenchmarks to understand in detail what you need to change. So far we've been talking about startup performance, but proxies spend a lot more time moving packets around than they do initializing. So we need also application load test infrastructure. And when you're building a really high-performance system, when you have a really well-performing proxy like Envoy, you also need a really high-performance piece of test infrastructure in order to adequately measure it. You want one with really low jitter. You want one that can handle the HTTP2 protocol, which has some different performance characteristics in many ways. And we, of course, on our team, were really busy building load balancers and improving Envoy's control plane and other things, and we really wanted to bring in somebody to help us evaluate what the next step should be that had a lot of experience with this. So we contacted Otto van der Schaaf, who will take us through the load generator.
Yeah. So we knew that that there was no tool out there that would satisfy all our requirements up front. Because most of them predate like H2 and large multi-core systems. So we were looking at something that we could modify and improve. And for that, we would need a code base that would be well tested, like Envoy's, and with a licensing scheme that would work for us. So we evaluated 10 existing tools. And based on the earlier requirements, we were able to narrow them down to 2, WRK and Fortio. So, while Fortio has some great technical properties, what we didn't find was H2 support or a community. Fortio had kind of like a different set of trade-offs. We also didn't find the community we were looking for, but there were also some the latencies it reported were kind of like less accurate than compared to WRK and control measurements, and we could pinpoint those to uneven request release timings and possibly garbage collection and Go scheduler unfairness issues. Sorry. So we ended up deciding to build a load generator on top of Envoy that would allow us to piggyback upon a networking stack that is being invested by a lot of people across a lot of companies. Concretely, HTTP2 support is in development as we speak, and once that lands, then Nighthawk would basically get that for free. And we also decided to make the tool visualization agnostic, so we would exploit existing visualizations, including Fortios. That new tool is called Nighthawk. Nighthawk resides in a parallel GitHub repository next to Envoy, and it's largely done using Envoy-style test coverage and CI. It's got a lot of great dials and switches to help us understand how a proxy or other HTTP2 stack can scale in a bunch of dimensions. It supports closed-loop mode, where when a request is issued, another one will not be issued until a reply from the server has been observed. And this mode strives to provide a consistent stress on the server throughout time. In closed-loop mode, Nighthawk will report how much time it was spent blocked waiting for the server to respond. In open loop mode, the load generator can send up multiple asynchronous requests without waiting for the server to respond. This is more like how browsers work, especially in HTTP2. In open loop, we strive to provide a constant workload to the server throughout time within configured resource limits. So in open loop, there's no blocking diagram. And instead, if the server can't keep up with the load, we may observe local connection pool overflows, meaning that the request is skipped, in this case, from the server's point of view. We can use Nighthawk to collect accurate data and export it to Fortio to visualize the long tail. In this case, the 2 millisecond long tail really was a test setup problem because we didn't pin the server to a specific CPU core. And the OS scheduler wasn't optimal in that case. So when we did that, we see the long tail drop from 2 milliseconds to 600 microseconds. So here we compare Envoy in direct response mode, and on the left side we have it running on 1 and 2 threads, and on the right-hand side we introduced an extra Envoy hop and also run it on 1 and 2 threads, and we can see that, well, clearly the multi-threaded Envoy is a good idea when you introduce an extra hop. Sometimes just looking at the global aggregated numbers doesn't tell all. In this case, the latency plot is an odd shape, which cannot be explained without looking at the underlying data. So here we plotted like the per worker output of Nighthawk using Plotly, and we can see that some of the connections ended up unevenly spread across different Envoy workers, and obviously the more busy threads show worse latencies in this case, and this explains like the weird global aggregated shape. Next we look at a comparison of HTTP1 versus HTTP2. And surprisingly, we observe HTTP1 to be faster than HTTP2 by 5 microseconds, and that's kind of unexpected because HTTP2 is a binary protocol and you'd expect that to be faster. So we didn't dig into this, but this is like an interesting showcase of why it's using accurate measurement tools can help gain insights into performance. So furthermore, Nighthawk supports Zipkin tracing, which can perform trace initiation, and that can help you gain insight into how a workload, how a distributed system behaves under certain workloads. Now, Nighthawk is a load generation tool and not a framework, but it has a variety of features to help make it easier to integrate into a framework, either as a server-controlled via gRPC or via scripting hooks such as replay and termination conditions. So with that, back to you, Josh.
Okay. Thanks, Otto. Okay, so to finish up with the last technique, I wanted to describe something that's maybe somewhat more speculative and crazy, which is using fuzzing as a performance tool. So fuzzing is not intended to be a performance tool. It's intended to find potential security problems. But it also finds among those denial of service vulnerabilities, which are really a flavor of performance issue where the data controlled outside the system can influence its performance. So in the Envoy fuzzing framework, which is hosted on ossfuzz.com, you get a big table of metrics out with all the fuzzers vertically and a whole bunch of data horizontally, of which I showed only a small subset here. You can imagine using this table kind of the way that a day trader would use a stock screen to pick out potential interesting investments. So in this case, a fuzzer that runs very slowly, less than 2 evaluations per second, and it reports a lot of timeouts, failures due to timeout, and it doesn't crash too much. I should say that crashing in fuzzers actually is not that unexpected. It doesn't mean there's a security problem necessarily or a problem with the code. Usually you're running fuzzers on a subsystem with preconditions, and when those preconditions are violated, you may get an assertion. So it doesn't mean that there's a problem, but it means that the fuzzer runs really slowly because the assertions take a long time to execute even when they pass, and if they fail, it really takes a long time for the fuzzing infrastructure to recover, and you waste a lot of your time kind of rebooting your system. The fuzzing infrastructure itself is slow as well. So if you're finding like less crashes than the other ones, like 7% and a bunch of timeouts, maybe it's a performance bug. So you get this automated notification that you had a fuzz timeout, and this happened to be an area that we were thinking a lot about anyway, which is the Envoy HP header class. And then you can pull up a flame graph from that, and there it actually shows the problem pretty clearly, that there was an n-squared issue with updating a count when new headers arrived. Similarly, it's almost always harder to find these problems than it is to fix them. The fix was relatively straightforward. This resulted in a CVE for an n-squared sensitivity. But the main point is that the fuzzer helped us kind of find this problem, and it could find other performance-related problems as well. So this is not a slam dunk. You know, as I've said, the Envoy fuzz tests are really slow for reasons having nothing to do with the performance of the actual code. So being able to kind of discern that would really help. The fuzzing, let's see, other reasons the fuzzers are slow are that they're built using mocks, and the mocks are slow because they're designed for functional testing and not for performance. But one of the things that I thought might have potential is the fuzzing infrastructure is actually built on code coverage, because it introspects the code coverage as it's generating patterns in order to try to guide the pattern generation to cover more code. So as long as it's doing that, maybe it could tell us whether we were spending time in the code under test or in the test infrastructure or in the fuzz tests. And then we could use that to help us screen out potential issues. Anyway, the goals are aligned, because if you write efficient fuzzers, there'll be better fuzzers for security too. They'll be able to find more cases, and we might also potentially be able to find performance problems. So next steps. I think the big news here is that we've put a ton of work, we meaning mostly Otto, but also the people that have been reviewing it, Harvey and others, and we've evolved what I think is the bones of a really useful performance tool that works with a modern architecture on top of the Envoy network stack, speaking HTTP2, and it will inherit the ability to speak quick in HTTP3 as well. There's still a lot of work to do. It is a load generator. It is not a load test infrastructure. It is built to be easy to integrate into a load test infrastructure, but we would love to have some more participation. Echoing Matt's earlier comments, I think that if we think this kind of tool is valuable, we would love to have more people participate in this, and please join us. It's GitHub, Envoy Proxy, Nighthawk. So fuzz testing for performance is more of a hope. I hope something gels out of this. I think that it would be potentially useful to find performance problems using this infrastructure, and I think its goals are also really aligned with the needs of the fuzzing for security. So with that, I thank you for your time, and I think we have a little bit of time for questions. Question?
There was a slide which mentioned Nighthawk in direct mode and Envoy in a proxy mode, I think. What's the actual difference there?
So in direct mode, it's Envoy.
You want to repeat the question first?
Oh, sorry, yeah. So the difference between Envoy in direct mode and Envoy as a proxy is that in direct mode, Envoy actually generates the response itself So, and when I introduce the extra hop, it actually loops back through an Envoy proxy.
Yeah, part of the Nighthawk package includes Envoy as an origin server for the purpose of generating test data for doing load tests. Question?
Have you looked at using profile guided optimization and how that would integrate with this performance testing?
Question is, have we looked into doing profile guided optimization and how that would work with this performance testing? Certainly the answer is yes. I don't think we've done that. We've prepared data based on that on top of this talk, but it seems to me like Nighthawk would be a great source of data for performance-guided optimization. You could also potentially couple that with replay data from actual logs. But yeah, I think that's a good direction to go.